Today we are going to cover the last section of Chapter 8, hypothesis testing about population mean. Firstly, the notation for population mean is mu, corresponding to the population mean mu. X bar is the sample mean. Yeah, X bar, the sample mean, is a good estimation for the population mean, both point estimate and confidence interval estimate. And today in this section, our focus is to test the claim regarding a population mean. Yeah, of course, we would have to use the sample mean. All right, so we have a process to test the claim regarding the population mean. But before we apply the process, we need to double check the requirement. The process requires the following two conditions to be met. This is number one, this is number two. Let's look at number one. Number one requires the sample has to be a simple random sample, the ideal representative sample. The second condition says either the population is normal or the sample you get has a size bigger than 30, or both of them are met. Both of the two conditions are met. So you might remember this condition, the second condition, is a condition for central limit theorem. Is a condition for the famous central limit theorem. Central limit theorem says X bar, the sample mean, as a variable is normally distributed with mean mu, same with the population mean, and the standard deviation is the population standard deviation divided by rho n. Yeah, you might remember that. Yeah. So when the second condition is met, that means the central limit theorem applies. All right. We are the focus is to our goal here is to test a claim about the population mean mu. That means we don't know the value of population mean mu, right? So when we do not know the value of the population mean, it's very likely or very reasonably to assume we do not know the population standard deviation as well. It's very rare that you do not know the population mean and you know the population standard deviation. So here in this section, we assume the population standard deviation is unknown. Is a very reasonable, realistic assumption. Since sigma is unknown, okay, since we assume sigma is unknown, oops. So this sigma, we cannot use it, okay? We have to change it to S, use the sample standard deviation to replace it. Once we replace the population standard deviation with the sample standard deviation S, the test statistic is going to be T distributed, not Z distributed anymore. Yeah, this is a Z. So if you standardize it, if you standardize X bar minus mu all over sigma rho n, yeah, this is a standard normal. Standard normal is also called a Z distributed, right? Yeah, Z distributed. Yeah, but since we have to replace the sigma with S, so we don't have a Z distribution here. Instead we have a T distribution. Yeah, T distribution, you might remember in previous chapter we introduced the student distribution. T distribution here is the student distribution. So the process that tests the population mean mu is a t-score. It's a t-score. So in a calculator, when we need to test the population mean test a claim about the test population mean, the function what we gonna use is a t-test. Yeah. So first, I want you to remember that. All right. Yeah. The reason I already explained just now, sigma is unknown because mu is unknown, right? Yeah. So this z score doesn't work anymore. We have to replace the sigma with s. Then that expression, that variable becomes a t-distributed variable. T-distributed variable. So the test we are going to apply here is a t-test. Very important, is a t-test. All right, yeah. So use a t-test to test a claim regarding population mean mu also has two different methods. The first method is the critical value method, the traditional method. The second method is the p-value method. Both of them we covered on Tuesday when we learned how do we test a claim regarding the population, regarding a population proportion. We had two methods, right? In this section is the same thing. When we test for mu, we also have those two type of methods, and those two methods are equivalent. In a sense, they always give you the same result for the same sample. Yeah. They would both tell you, are you gonna reject null or fail to reject null? All right, so that's something preparation. Yeah, very important. We need to remember for testing population mean mu, the test we are going to apply is t-test, not z-test anymore. Is a t-test. All right, so we are going to go over some examples and to get familiar or to learn and reinforce the process. Let's look at the example. Example 1. Use technology to find a p-value for the hypothesis test described below. The claim is that for a smartphone carrier's data speeds at airports, the mean is mu equals 19 Mbps. The sample size is 21, and the test statistic is t-test, so it's t. Yeah, t-score. T equals negative 2.526. Okay, yeah, the test statistic is t equals negative 2.526. All right, so this question, if you attempt to use t-test in the calculator directly, you are not able to find a p. The intention of this question is want you to use the t-distribution. Remember the relationship between t-distribution and the z-distribution. Their curve very similar. Okay, yeah, it's not close. Is open, by the way. When the sample size approaches infinity, t-distribution approaches to standard normal distribution. Yeah, this is t. Since our sample size is 21, yeah, very important parameter about t-distribution is the degree of freedom. Degree of freedom of t-distribution is n-1. In this case, n is 21, the sample size. So n-1 is 20. So this is the curve of a t-distribution with degree of freedom equal to 20. All right, yeah, so let's look at the original claim. Yeah, always start from original claim. The original claim is the mean is 19. Yeah, let's ignore the unit. Yeah, so our original claim here is mu equals 19. Can we create or construct h sub 0 and h sub 1 based on the original claim? We know that no h sub 0 always has to contain an equal sign, right? So actually in this case, our original claim, and the null is the same, mu equals 19. And I want you to help me to determine what's H sub 1. What's the alternative? We need to know the alternative hypothesis in a symbolic form in order to determine is the t-test going to be a left tail test or right tail test or two tail test. Yeah, I want you please read the question. Is in the question and tell me what's the alternative. Bigger than, less than, or not equal to. Yeah, only those three options. Hello? Very quiet. Am I clear my question? Yeah, so what is the alternative in this case? Yeah, exactly. Melinda, yeah, not equal. Leah, you are right as well. Is not equal to is a two-tailed test, all right? Yeah, is a two-tailed test. Very good. Mu not equal to 19. Perfect. Yeah, since the alternative is mu is not equal to 19, this is a two-tailed test. Very important. We have to know is a two-tailed test. Yeah, what kind of test? In order to draw the graph, in order to draw the critical region, right? Yeah, so it has two critical region, like half of it is on the left tail, half of it on the right tail. Yeah, but you know what? Actually, we don't really need that in this case because the goal of this question is to find the p-value. Yeah, so the goal of this problem is to find the p-value. Now, how do we find the p-value? Yeah, we do need to know this though, okay? Yeah, we just do not need to know the critical region. Yeah, so for a two-tailed test, let's look at here. For a two-tailed test, critical region in two tails, the p-value is twice the area in the tail beyond the test statistic. Yeah, let me show you how do we find the p-value when the test is a two-tailed test and the test statistic fall in on the left tail. Okay, in this case, our test statistic t, suppose right here, is negative. Remember, t distribution is centered at 0. Same with the z distribution. So here's 0. Yeah. So test statistic t negative 2.526 is around here. Okay. Yeah, is around here. Negative 2.526. All right. So we are going to find the area to the left of this test statistic. Very extreme, like a significantly low, the chance. The area of the shaded region represents the probability or chance getting the samples that give you the statistic as least extreme as the statistics we get here. But that's not p-value. P-value is twice of that area. Okay, we have to multiply 2 later. Yeah, just remember that. Two-tail test right here. For two-tail test, p-value is twice. Very, very important. You remember that. Because the two-tail, right? Yeah. So besides the one statistically significantly low, you also have a significantly high. Yeah. So you have to double it. Yeah. So p-value is twice the area in the tail beyond the test statistic. So in our case, it's twice of the area of the shaded region. Okay. Then how do we find the area of the shaded region? We are going to use so we are looking for the probability, right? So we are going to use the TPDF function in the calculator. All right. Yeah. So you ready for the calculator? Yeah. Turn on your calculator. A TI-84 calculator, very useful for the class. My experience is students love the calculator, and it's like yeah, it can make your job a lot easier instead of manually calculating everything. So let's go to second verse. TCDF is, on my calculator, is number 6. TCDF. Oh, my bad. Did I read it wrong? PDF is the like micro, not like a file. My bad. I mean TCDF. Okay, CDF. Something's wrong with my stylus. TCDF. Okay, TCDF. On my calculator, number 6. Let's select that and look at the region. The left bound is negative infinity, so the lower bound is negative infinity, negative double E 99. Upper bound is negative. Please remember, use the negative sign in the parentheses on your calculator. Yeah, very bottom right corner, the key. Yeah, do not use minus sign. Otherwise, you will receive error. You have to quit, right? Yeah, so negative 2.526. Yeah, DF. What does DF mean? DF means the degree of freedom, right? Yeah. Degree of freedom is the sample size minus 1. In this case, it's 21 minus 1, so it's 20. So we enter 20. And then paste. I have the area is 0.01004245557. Yeah, let me know. Do you have the same thing with mine? And do you need me to repeat the process of applying TCDF? Not PDF, I apologize again. CDF, okay, CDF. Cumulative. What was lower and upper? Yeah. Okay, let me repeat that. So we go to TCDF. The lower, look at the region, Charlene. The is from negative infinity to negative 2.526, right? So your lower is negative E99. It represents negative infinity. Yeah. Negative sign is on the bottom right. Yeah, double E is the second comma and 99. And the upper, okay, that means thank you, right? Yeah, you are welcome. The upper limit, upper bound, yeah, negative 2.526. Yeah, you would receive same amount. Okay, hold on a second. Don't forget, that's not our p-value, okay? What is our p-value? Our p-value is twice of that value, okay? I'm going to, since I already have that value on my calculator, I just continue from there by multiplying by 2. You don't have to enter it again. Yeah. The more familiar, the more time you spend with the calculator, the more familiar you are with the calculator. So it's 0.0200849115. Yeah. So a round number as needed depends on the requirement of the question. All right. Yeah. So that's about it. It's just a part of the process. Yeah. Just a part of the process. In order to make a conclusion regarding the no and the final formal conclusion about the original claim, we need alpha. At least we need alpha, right? But alpha, remember, is subjective, something subjective. You determine, you decide that as a researcher. Based on the research you are going to do. Yeah. Any question about that? Yeah, p-value. How do we find a p-value for two-tail tests? This not only apply this method not only apply for claim regarding population mean. If the claim is about the population proportion, like Tuesday. Yeah, although we learned that it's the same thing. Yeah, p-value always equal to twice of the area. Yeah, beyond the test statistic. All right. Any question about that? It's pretty tricky. If you make the alpha very small, then p flies. If you make the alpha like 5% a little bit bigger, then you reject the null. So really, the decision decide what's alpha really very important. Yeah, when you do your research in reality. How do you figure out what the tail is? Okay, that's a good question. To figure out what type of test, like left tail, right tail, or two tail, we look at alternative. Yeah. So your course question actually is how do you know the alternative is not equal to, right? If the alternative is bigger than, that's right tail. Yeah, always look at the alternative for the type of tail. Yeah. If the alternative is less than, then is left tail. If the alternative is not equal to, then that is two tail. So now let me answer your question. How do we know the alternative is not equal to, right? Yeah. So read the question. The question shows hints that the claim is a smartphone data speed at the airport, yeah, the mean equal to 19. Sample size is 20. It doesn't say anything else. It doesn't say more than or less than. In that case, is a double. It's more reasonable to assume the alternative is double. Is not equal to, sorry, is not equal to. Let me know, did I answer your question? Yeah, in order to know what type of tail, we have to know what type of alternative. In order to know what type of alternative, we have to read the question. Is in the question actually. We do not have any, the question doesn't say anything about bigger than or less than. Then that's gonna be not equal to. All right, did I answer your question? Yeah, okay, no problem. All right, so that's the first example. Let's now go to second example. Second example is the same, similar with the first example. The requirement is the same as you can see. Use technology to find the p-value for the hypothesis test described below. Yeah. The difference is, of course, different, right? Yeah. The original claim is for 12 a.m. body temperatures, okay, the mean is bigger than, okay. So in this case, our original claim is mu is bigger than 98.6. Yeah, based on the original claim, let's construct null and alternative. Remember the null has to be equal to, right? Yeah, I have repeated so many times, so please remember that. Yeah, null has to be equal. Yeah, the null is correct, is the assumption of the whole process, is the logic behind the whole process, the hypothesis test. Mu equal to 98.6. All right, now what's the alternative? Yeah, another thing very important about this piece, this component, this part, is the original claim has to be either equal to null or equal to the alternative. Yeah, our original claim either this is the same with the null or is the same with the alternative. Of course, in this case, the original claim is different from the null. So that means the original claim has to be the same with the alternative. So that's how do we know the alternative is bigger than 98.6, right? And since the alternative is bigger than, what type of tail this is? Yeah, please type what type of tail this is. Yeah, exactly. Thank you, Leah. Right tail test. Right tail test. So here we're gonna have a right tail t-test. Okay, right tail t-test. T-distribution, T-curve. Very similar with the Z-curve, yeah. Centered at 0. Since we have a right tail test, the p-value is gonna be, you can look at it here, yeah. For right tail test, the p-value is gonna be the area to the right of the test statistic. The probability is actually conditional probability. Assume the no is correct, then the probability that you get sample statistic as least as the test statistic you have from the sample you just get. All right, our test statistic is given 2.662. Yeah, so is let's say is here. It's around here. So t equals 2.662. Right tail test, right? Yeah, so shaded region to the right of the test statistic, and that area, the area of the shaded region, would be our p-value. Okay, yeah, you don't have to multiply by 2, by the way. Only when the tail is a two-tail test, only when the test is two-tail test, you multiply by 2. For one-tail test, you don't multiply by 2. Okay, yeah. All right, in order to know the area here is a probability, right? Yeah. We need to use, this is T distribution, by the way. Let me label it. T distribution, what's the sample size? Sample size is 4. So the degree of freedom is 3. Yeah, T of 3. So the function we are going to apply in the calculator, same with earlier, is T CDF. Yeah, C here means cumulative. Is the density curve of T distribution. Under the density curve of T distribution, you accumulate from 2.662. You accumulate little by little continuously all the way to infinity. Yeah, cumulative function. Yeah. All right. Let's go to calculator. Turn on your calculator. Let's go to second verse. My calculator is number 6, TCDF. So this time, let me write it down. The lower bound is 2.662. Yeah, your accumulation starts from 2.662. Yeah, always from left to the right. And then your upper, the reason because the x-axis, the horizontal scale, the real number line, when you look at from left to the right, the number getting bigger and bigger. The upper is going to be positive infinity. And how do we express positive infinity in calculator? Double E 99. Yeah, we have done this many times. So let's enter 2.662. And upper is a positive. You don't have to enter positive, just a double E, second comma, 99. DF, again, degree of freedom. Our sample size is 4. Degree of freedom is 4 minus 1, 3. So enter 3 there, and then paste. The number I got is 0.3. 0.03. Yeah, 0.03. 0.038.104.2339. Let me know, do you have the same thing? Yeah, p-value around 3.8%. Yeah. Again, depends on your significance level. Awesome. Thank you guys. You guys are great. Depends on your significance level, right? Then we know if this is significantly high or not significantly high. All right. Yeah. So I do not have a same type of question with the left tail, but I think should be enough. This one is double tail. Yeah. In double tail, this is not x. Okay, it's multiply. Multiply. Yeah. The first question is two-tailed test, how do you find the p-value? And this one is a one-tailed test. Yeah, use the right tail as the example. Right tail test, how do you find the p-value? Well, if we have a left tail test, that would be the same, okay? Yeah, do not multiply 2. Only for two-tail test, you multiply 2. Yeah, so I hope we can have a better understanding about p-value through those two examples. Also, I think it's necessary to cover it, especially the first one. Many students would forget to multiply by 2. All right, so that's the first two examples. Now let's move on to example 3. There's a lot to read. Let's see. A data set about the speed dating includes like readings of male dates made by the female dates. The summary statistics are, so this is the information about the sample, right? You are doing research, of course you have to get a sample. Yeah, those information from the sample size, sample mean, sample standard deviation. And this is your predetermined significance level. That's very high, 10%, significance level. To test the claim, we should be able to find the original claim here, that the population mean of such readings is less than 6. Okay, let me write it down. Yeah, when I read the questions, at the same time I would take notes on my scratch paper. Yeah, original claim is the mean mu is about the population mean mu is less than 6. All right. And then from the original claim, we are able to have our no and alternative. Again, no always only can turn equal, so the no is mu equals 6. Yeah, you also have plenty of similar practice, so you should know the no always only can turn equal sign. So here in symbolic form, the no hypothesis is mu equals 6, and the alternative is mu less than 6. How do we know that? Again, the original claim is either equal to the no or exactly the same with the alternative. Since the original claim is not equal to the no in this case, the original claim has to be the same with the alternative. So alternative here is the original claim. So as we can see, this is going to be a left tail test. Yeah, we have a two tail. Example 1, example 2 is a right tail. Example 3 is a left tail. It's going to be a left tail t-test. Okay, left tail t-test. Assume that a simple random sample, okay, that's a requirement. Yeah, technically we really should always check the condition, the two condition. Sometimes we forget because the question is designed. They are designed already satisfy those. So unless it is pointed out, you remember that. So sometimes you might not remember that. But here, a simple random sample and identify the known alternative. Sample size, what is sample size? Oh, 197. So the central limit theorem requirements are satisfied as well. Yeah, it doesn't matter if the population normally distributed or not. Sample size is large enough for us to apply the process. Okay, identify the null and alternative, test the statistic, and the p-value, and state the final conclusion that addresses the original claim. Okay. Let's manually do at least one question. I promise in future sections, when the formula is very complicated, I will not make you to even use the formula at all. Yeah, but this is the first time we do the test for population mean mu. We at least have to use one time, okay? Yeah, so the test statistic formula T is that. Okay, x bar minus mu all over S over root n. So let me write it down. Test statistic t equals x bar minus mu. The mu here is our claimed mu in the hypothesis over S over root n. Okay, yeah, at least we have to use one time. And we are going to figure out what is t and t sub alpha in order to apply the critical value method to make the decision about the no. Yeah. So let me draw the t curve again. In this case, our significance, our critical region is on the left tail. Yeah. So this is going to be our t sub alpha, and this is the critical region. Okay, critical region. No, I don't want to use this color. Just use the black color. This is T sub alpha, and this is the critical region. Okay, critical region. And we are going to separately to find what's the test statistic and what is the critical value, and then we're going to compare them to see if the test statistic fall in the critical region or fall in the blank region. That's the plan for critical region test of a method. Okay, yeah. So let's see, how do we find the critical region? The area of the critical region is 10%, 0.1, very large. Right? Yet knowing this curve is not Z curve, it's T curve. We're doing T tests. The T curve has a degree of freedom 196. All right, 196. Yeah. Degree of freedom is n minus 1. N sample size is 197 minus 1 is 196. Okay, so how do we find the T alpha? Yeah, also I need to show you this, so we really need to do this at least one time. We are going to use inverse T function in a calculator, all right? Inverse T function in a calculator. Let's go to the calculator. Turn on the calculator and go to second vars. My inverse T is number 4 on my calculator, INVT. I select that function and I would see 3 entries. I see area, I see df, I see paste. Actually, only two entry. Only 2 entry. For the area, we are going to enter 0.1 because that's the area to the left of the critical value, right? 10%, 0.1. Be very careful. I noticed that that's actually a common mistake. Sometimes the significance level is 0.01, 1%. Sometimes 0.01, 10%. Yeah, please look carefully. Make sure the value is correct. Yeah, in this case the big one is 0.01, 10%. The F is 196. Go down 1 and then paste. And the critical value I got here is negative. It's supposed to be negative, right? Yeah. Negative 1.28588,577, right? Do you have the same critical value, guys? Probably yes. Awesome. Very good. Thank you. Very good. So we got a critical value found. Now let's find the test statistic. Okay. Test statistic. Let me see if I can move this here. Yeah. So test statistic. We're going to enter the value. That's the formula. X bar is given 5.57. Mu is given. Mu is the one in the claim, 6. And the denominator S 1.87 divided by root n. So square root 197. All right, so on my calculator, this is what I do. I enter 5.57 minus 6 and then enter. Okay, enter. Yeah, let me just say it. Yeah, we enter. This is what I do. Let's go in the main page, like a main screen of the calculator. I would enter 5.57 minus 6, enter. Now I have a negative 0.43, and I'm going to divide it by, I'm going to use a parentheses, left-handed parentheses, and then enter 1.87 there, and then divide by, yeah, in the parentheses, I'm going to divide by another slash, and use the second x squared. So I have a rule, and in the rule I have 197. And then close the parentheses. Let me write what I have here, okay? Yeah, I have a negative 4.3. Sorry, negative 0.43. And then I divided by, so I have answers slash, this is what I enter in the calculator. I get a left end of the parentheses and then 1.87 and divided by, this division is in the parentheses. Yeah, square root 197 and then close the parentheses. Yeah, if you have that same thing with mine, and you should have the test statistic equal to negative 3.227453264. Let me know if you have the same thing. Play with your calculator. Find the best way for you. Yeah, find the best way. Awesome. Yeah. Find the best way that you feel you're confident. Yeah. The way that process you apply always give you the right answer. Yeah. That's why we need to practice, right? Okay, let's see, where is this test statistic fall? Is 93 point-ish. Okay. So turns out it fall here. It fall here. Right? Fall in the critical region, because 93 point-ish is less than negative 1.285A, you know, the critical value. The test statistic is to the left of the critical value. So because the test statistic fall in the critical region, that means the rare event occurs. I was guessing it's probably because 10% is so large. Yeah, so it does. Yeah, so the fall in the critical region, that means rare event occurs. That means our assumption that the null is true is false. So we decide to reject the null. Okay, yeah, we decide to reject the null. That's what we conclude about the null by using critical value method. All right, by using critical value method. And how do we use the p-value method? Manually is like before. We are going to find the area of the region to the left of the red bar. Yeah, this is the p-value. Okay, this is the p-value. I know the picture drawings are not very pretty. Yeah, so this red region, the area of the red region to the left of the test statistic is the p-value. Yeah, let's see what do we have by using the technology. We're going to use TCDF, right? We have actually done that part twice earlier. This is double or two, I'm sorry, two tail. This is a right tail. This is a left tail. Okay, let's do the left tail. So the p-value is the probability that the t-score is less than what is it? Negative 3.227453264. Yeah, so that's why we need to use the TCDF function in the calculator to figure out the p-value. Yeah, let's go to second verse. TCDF number 6, TCDF, and lower is a negative infinity, is already there. On my calculator is already there. Upper is negative 3.227453264. I'd like to make it as precise as possible. Degree of freedom, sample size is 197. So 196 is the degree of freedom. And I got this area, the p-value. This is what I got, okay? P-value I got is, to see if you have the same thing, 7 point, don't rush, don't just look at 7.3. Look at the right side, look at the whole thing. 0.13862 E94. Yeah, do you see the Z94? The E94. So the p-value is a tiny value actually, 0.001207. Yeah, let me just round it a little bit. Yeah, 0.0007. Let me know, do you have the same p-value? We actually practice all the three types, right? Two tail, right tail, here is the left tail. Yeah, p-value is a tiny number, 0.0007. Of course, it's less than alpha. Alpha is 10%. Remember, it's a very large number. So when the p-value is low, no must go. So one more time, again, we decide to reject the no. Okay. Last step of the process is to make a formal conclusion about a no. Okay, make the normal conclusion about the no. Sorry. Make the formal conclusion about the original claim. Yeah. So in this case, we reject no. Reject no. We reject no. So we can say we have sufficient evidence to support our original claim. Yeah, because we reject no. Reject no, we have sufficient evidence to support our original claim. Yeah, it's correct, but we can also double check by looking at the table that I gave you. Where's the table here? Yeah, I will include the table for that. So original claim is the alternative. Yeah, there is sufficient evidence to, yeah, it's correct. And that actually is the only one case in which we say I have sufficient evidence to support a claim. That's the only case. Only case. Let's go back, 8.3 here. And that's the whole process, okay? I hope you had fun. To be honest, sometimes I only use a calculator. I don't even draw the graph. I just enter the thing in the calculator. It's kind of like boring, no fun at all. Yeah, so at least make yourself go through a few times the process manually. And for the test, if you can use a calculator, yeah, let's use a calculator. There's a faster way. Let me show you. So in the calculator, we are going to go to t-test to find the test statistic and the p-value quickly. Okay, quickly. So let's go to stat. And then go to the right twice. Select tests. In the drop-down menu, we have t-test. The number two is my t-test. And then confirm that. And you are going to select stats because we do not have the raw data in this case. You can see you have data and stats, right? Yeah, please confirm stats. And once you confirm stats, you would see the entries that we need to enter value for, the variables. You see mu sub 0, you see x bar, you see s sub x, you see n, you see mu, yeah. Is mu not equal to mu 0? Yeah, the type of the test or less than mu 0 or bigger than mu 0. And the last one, last column, last row is a calculate. Okay, yeah, I never use the draw. Okay, so let's see what do we enter for those variables. Mu sub 0 is 6 from the claim. X bar is given 5.57. S sub x also given 1.87. N is also given 197. What fun for this? You just enter everything there. So we have a left tail test. So you have to confirm this one. Okay, not just blinking. Make sure when you move to the next row is really highlighted, selected, and then calculate. Okay, let's do that. Mu sub 0 is 6. X bar 5.57. S sub x 1.87. N equals 197. Okay, choose the left tail, so in the middle, the one in the middle, okay? And calculate. All right, so you should see this. What I have here is I have mu is less than 6 here. T equals -3.227453264. I have p value. This is capital P, by the way. P value is 7.32013866. E -4. I also have x bar. X bar is already given, right? 5.57. S sub x, just repeating information. N equals 197. So let's compare the test statistic and the p-value from the calculator with our answer. This is our answer earlier manually. It's not actually manually. We also use the technique. It's the same, right? Yeah. If there's any, yeah, it's exactly the same. And this one, test statistic right here, -3.227. Yeah, it's the same, exactly the same. All right. Am I clear about the technology? Well, for the test, for the homework, since we already practiced, you can just use the function t-test. Let me know, do you have any questions? But to be honest, as I said, no fun. You just enter everything there. What's the fun? So I really, again, please, go through like at least a couple of times the process, and you have a very good feeling about the test, hypothesis test. Otherwise, you really just use the function, enter the entries. It's very dry. Okay, so now let's move on to the next question, example 4. This is a very long question. In a test of the effectiveness of garlic for lowering cholesterol, 81 subjects. So when I read the question, I take notes. 81 subjects were treated. Okay, don't rush. 81 was treated with raw garlic. Cholesterol levels were measured before and after the treatment. The changes before minus after. in their levels of LDL cholesterol have a mean of 0.9. Okay, so let me for now write n equals 81. This sample mean, right? 0.9. Sample standard deviation S 22.7. So that's, I really like take notes. Use it 0.01 significance level. So be careful. This is not 0.1, 0.01, 1%, pretty small. To test if the claim, okay, original claim. With garlic treatment, the mean change in that is greater than, okay, so original claims mu is bigger than 0. What do the results suggest about the effectiveness of the garlic treatment? Yeah, assume that a simple random sample. So those conditions are conditions. Simple random sample. Our sample size 81 is bigger than 30, so we're good. Okay, we're good with that. Identify null and alternative, and test the statistic and the p-value, and see the final conclusion about the original claim. Okay, so the previous question, those entry gives you, right, n x bar s, you really don't have to make much effort. But this question, you really have to read the question to take notes to identify the sample information n x bar s, right? Okay. So we are not going to go over the whole process. We are going to just use the technology, the t-test here, okay? T-test for this question. Let's go to stat. Let's reinforce the, this method. Yeah, TI-84 calculator method. Go to stat, tests number 2, t-test. And let me know if you still remember it. Yeah, mu sub 0. When you see mu sub 0, oh, my bad. What I'm doing now? I'm not finished this yet. Let's finish this. We don't even know what type of test that is. So mu equals 0. Sorry, mu equals 0 is gonna be the null, because the null always have to contain equal sign, right? And the original claim, this case, equal to the same with the alternative. Yeah. So this is a right tail test. Right tail t-test. On my scratch paper, I would write that to remind me. I'm going to use a t-test. All right. So on a calculator, mu sub 0 is gonna be 0. X bar, sample size, sample mean 0.9. S sub x 22.7, 22.7. N equals 81. We're gonna do right tail, so it's bigger than mu sub 0, and then calculate. Yeah, make sure you have those taken care of in a calculator. This is 0. This is 0.9. This is 22.7. This is 81. Bigger than mu sub 0. Calculate. Okay, so I'm not going to write everything on the screen. I'm going to only write T, the test statistic, and the p-value. Okay, this is a test statistic. This is a p-value from the calculator. My test statistic is 0.35, 68, 28, 1938. My p-value is 0.36, 10, 799, 556. Yeah, let me know, do you have the same thing? We don't have to use the formula, right? Same thing. Awesome. Thank you. Awesome. Yeah. Okay. So then we can go through both methods to see should we reject no or fail reject no. Yeah. So well, I always do the p-value first. Yeah. Alpha is 1%, 0.01. As you can see, p-value is high. No must fly, right? Yeah. So we should fail to reject. No, the two methods are equivalent. So when we use the critical value method, we do still have to draw the curve. Yeah. Suppose we have to use the critical value method, we still have to draw the curve. It's a right tail test, so T sub alpha fall in a right tail, and the critical region has area 0.01, very tiny. Very tiny. Yeah, this is T80. Yeah, because the sample size is 81. Degree of freedom is 80. Yeah, so if we go to inverse T function, we are able to find the value for the critical value. Yeah, so we go to second verse, inverse T number 4. Okay, so inverse T number 4, the area we are going to enter is not 0.01. It's gonna be 0.99 because it's accumulating from the left. Yeah, this area is 0.99. Yeah, and the DF is 80. And the critical value is 2.37. Yeah, suppose you have to go through the critical region method, you do have to draw the graph and find the critical value, because the critical value method, of course, use the critical value. You have to compare your test statistic with the critical value. So your test statistic inverse T 0.99. 2 point 0.35. This is 0, right? Yeah. 0.35 is very close to 0. Yeah, the test statistic is very close to 0. It's right here, right? Yeah, it should be pretty far away from the critical value. So obviously, the test statistic fall in the blank region. Yeah, very close to 0, far away from the critical region. Yeah, again, this method also tell us we should fail to reject no. All right, yeah. Sometimes I don't even do the critical region method unless the question requires to, because the p-value is so convenient. And those two methods are equivalent. Yeah, you got a p-value, you got a alpha, compare. P-value is low, no must go. P-value is high, no must fly, right? In this case, no flies. So we fail to reject no. Formal conclusion. We fail to reject no. So fail to reject no. That means there's a chance the no is correct. All right? So we do not have sufficient evidence to support the claim, the original claim that mu is bigger than 0. Does that make sense? Yeah. So fail to reject no. Yeah, but we cannot just say Because we fail to reject no, so it means there's a chance that the no is correct. So we do not have sufficient evidence to support the alternative. Yeah. Let's go to the table again. This is this case. The first case. All right. Yeah. There isn't sufficient evidence to support the original claim. The original claim is the same with the alternative. All right. So that is example 4. Yeah. Previous example is reject no. Here is fail to reject. On the test, will be questions on critical value? It depends on the way the question is designed. For example, it has many parts, part A, part B, part C, part D. If one of the parts asks you to give the value of the critical value, then you would have to go through the curve and inverse t to find the critical value. Draw the graph. I would say you would have something like that. Depends on how the question is designed. Yeah. Yeah, for sure. Critical value very important. Did I answer your question, Melinda? Yeah, you would have to. Yeah, you would have to know the process. Like draw the graph, find the critical value by using inverse t. In this case, on Tuesday is inverse normal, right? Yeah, it's different, depends on the distribution. All right, so last example. Let's see if my time management is good. We have 10 minutes for that. Assume that a simple random sample, okay, condition 1, satisfied, has been selected from a normally condition 2, yeah, the central limit theorem requirement satisfied, and test has been selected from a normally distributed population and test the given claim. Okay, identify the known alternative hypothesis, test the statistic p-value, and state the final conclusion that addresses the original claim. A safety administration conducted crash tests of child booster seats for cars. Listed below are results from those tests, with the measurements given in standard head injury condition units. The safety requirement is that the HIC measurement should be less than. Okay, that's useful. Yeah, the requirement is less than 1,000. Use that significance level to test the claim that the sample is from population with a mean less than, okay, OC. Original claim, mu is less than 1,000. All right. Yeah. Other information from the problem is alpha equals 0.05, right? Yeah. And we only have a sample. We don't have the sample size so small. 1, 2, 3, 4, 5, 6. But you know what? Doesn't matter. Because the population is normally distributed. Yeah. Okay, so original claim is identified. No and alternative. No is always equal. Alternative is the same with original claim. In this case, mu is less than 1,000. Okay, so this is a left tail test, right? Left tail test. Okay, so let's use a calculator. T-test. Yeah, let's go there. But in this case, we have to use data. Okay, we don't have a sample mean, sample standard deviation, so we have to use data. But before we use data, let's go to here. Let's go to stat and then add it and then store our values in L1. Let's do that, okay? Go to stat, add it. Yeah, I have some history data. I'm gonna erase them. Okay, in L1, I'm gonna enter those 1, 2, 3, 4, 5, 6 values. Yeah, I have 775, 642, 1073, 589. I'd rather slow down than making any mistake. 538, 613. And sometimes I do spend time to double check because, to be honest, this is all you need to do, right? If you use calculator, that's really all you need to do. 775, 642, 1073, 589, 538, 613. Okay, awesome. All right, guys, do you have the values entered in L1? Yeah, I use L1. Your choice. We have 6 lists in the calculator. I do L1. And now we can go to stat, tests, and go down to select t-tests. And this time we're going to highlight data. Okay, you should see this. You should see the data here. And once you confirm the data, you will see mu_0 and list and frequency, and then mu, the type. The type is a two-tailed, left tail, or right tail, and then calculate. All right, yeah. So our mu_0 is 1000, is from the claim. Our list is L_1. Yeah, how do we enter L_1? How do we enter L_1 there? We do second number 1. Okay, on 2 keys. Yeah, second key and 1 key. So you would have L1 there. All right, so let me enter that. mu_0 is 1000. L1, second 1. I notice if I do not enter 1 for frequency, it doesn't let me go down. That's my calculator, so just leave 1 here. We don't have a frequency list. Just put a 1 there. Sometimes if the data is a lot and it is sorted as a frequency distribution table, then we need that, but we don't have that in this case. And then I'm going to choose, this is the left tail, right? Confirm left tail. So right here, confirm left tail. And then calculate. And I'm going to only write down my t statistic, task statistic, and the p-value, okay? Task statistic I got is 93.66747,902. And my p-value is point, very tiny, 0.00724, 0.6975. Yeah, let me know, do you have the same thing? Awesome, guys. Very good, very good. Perfect. Yeah, let's see. Okay, perfect. Very good. You know, we only have 3 minutes, so I'm going to skip this. Yeah, but I would like you finish. Okay, is left tail, so our alpha fall here. alpha is 0.5, yeah, you would be able to use the inverse t to find your critical value. Yeah, this is a t distribution with degree of freedom equal to 5. Yeah, very low. And you would be able to find this value. Because of the time is limited, I'm not going to do that here. But I would strongly recommend you do it. Okay, yeah. Let me highlight this part. And then you're going to compare our test statistic with the critical value. And here I'm going to use the p-value method to compare our p-value with alpha. Alpha is 0.05. So p-value is low or high? Low, right? Yeah. P-value is low. No must go. We're going to reject the no. Reject no. Okay. So reject no. Then we would conclude there is sufficient evidence to support our original claim that the mean is less than 1,000. That means it's safe, right? The sample shows in general in the market that kind of product is safe, meet the standard. Okay, that's my understanding. All right, guys, is that clear, everybody? Yeah, please don't forget to email me the questions you want me to cover, especially you want to make your test 3 more convenient or easier by having the formulas you want me to include, you have to email me, okay? Email me, I'll include that email formulas in the email formula sheet. Okay, let me take a picture of the attendance and we can call it a day. When we get to the end of the semester, you can see I feel like the content actually is getting easier, especially with the technology. All right. I'll say good night now. Feel free to email me if you have any question. Bye, everyone. Good night.